In this lesson, we're looking at the equations and graphs of exponential functions. And we start by just exploring the graphs and seeing what are some key features that we have. So I'm going to zoom in on this first graph for a moment. And let's look at some of those key features. We've seen the domain a lot. So as I examine the domain of this, every x value is included in this domain. So we're looking at every x from negative infinity to positive infinity. The range of that is impacted by this horizontal asymptote. We can see that the function is going towards -6 on the left side. So it's getting closer and closer to -6 and leveling off. That is a horizontal asymptote. So the range is going to be impacted, and it would be -6 to positive infinity. The y-intercept, we can see, crosses right here at -4, so the y-intercept is 0, -4. The x-intercept is not exact, so we'd have to estimate, but it's a little bit before +3. So we might say the x-intercept is 2.7 or 2.8, maybe. We're just estimating. We did see a asymptote. This has an asymptote at y equals -6. And then we're going to look at end behavior again. Now, end behavior just describes what's going on the ends of the function. So as x goes to negative infinity towards the left side, the y values are approaching that -6. The function is approaching -6. On the right side, as x goes to positive infinity, as x increases, the y's are just going to keep going up positive infinity. So now we have a second graph here. It's still an exponential function. Its domain is negative infinity to positive infinity. The range of that function is impacted by the asymptote. There's a horizontal asymptote. We can see it level off at +2. So the range of this function is 2 to infinity. Notice I'm not including that 2, and that's because there is an asymptote at y equals 2, that horizontal asymptote. The y-intercept we can see is +5, so 0, 5. And then because this function is approaching that horizontal asymptote, it never crosses the x-axis. So this one does not have an x-intercept. So the x-intercepts don't exist, or there are no x-intercepts. The end behavior is looking at what is the function doing on the ends. So as x goes to negative infinity to the left, this function is going to keep going up and up and up. So it's approaching positive infinity. On the right, as x goes to positive infinity, the function is approaching the value of 2. So y is approaching 2. Every exponential function kind of holds these same shapes. So we can see an exponential growth pattern or an exponential decay pattern. It's growing when the base of that exponential is bigger than 1, but it's decaying when that base is between 0 and +1. We're never going to have an exponential function that has a negative base. The base is always positive. Now we can use transformations to describe changes to a exponential function. So let's look at the parent function that we graphed a few weeks ago when we were doing that initial parent function lesson. So if I look at the graph of 2 to the x power, if I'm not sure how to graph it, I can always do an input-output table and make that general graph. We can see what's happening as x kind of changes from negatives to positives, so I can just plug in some different numbers. I know 2 to the 0 power, if x was 0, would be +1. 2 to the first power is +2. 2 to the second power is 4, and 2 to the third power is 8. So there's some section to the right of 0. Let's look at to the left of 0. If x is -1, I have 2 to the -1 power. Negative exponents would make that 1/2. 2 to the -2 power is 1/4, and 2 to the -3 power is 1/8. So if I graphed this, we would have a graph that looks something like this. It is slowly increasing in the very beginning. It's very close to 0 on the left side of the graph, and then it starts to increase quickly, like an exponential growth we would, as we expect. Now, if I transform this using the graph y equals 2 to the x minus 3, that minus 3 is outside the exponential, so it's shifting down 3. Every single point goes down 3. That 0, 1 will go down 3 to 0, -2. 1, 2 goes down 3 to 0, -1. We had a point at 2, 4, down 3 is 2, 1. 3, 5. We can see that every single point has shifted down 3, but so has the horizontal asymptote. So the horizontal asymptote is now -3, and we have a graph that looks like this. It still maintains the same shape, but it's shifted down 3. All right. For the second graph here, we're investigating the parent function, 1/3 to the x power. Again, if we need to do a input-output table, we can create a table. We might want to look at what's happening on the left in the negatives and on the right in the positives. Anything to the 0 power would be 1. 1/3 to the first power is still 1/3. 1/3 to the second power would be 1/9, and 1/3 cubed is 1/27. If I do 1/3 to the -1 power, that negative exponent would flip that fraction to become +3. To the -2 power would be +9, and -3 would be +27. So we can graph some of these points. We're not going to be able to graph all of them, but we do see the general shape take form. And this is an exponential decay function. It is approaching 0 on the right side. So there is a horizontal asymptote. That one is at y equals 0. If we use our transformations, we want to reflect over the x-axis. And then go up 6. So we're taking that original equation and reflecting over the x, and then shift up 6. So if I take the point 0, 1 and reflect over the x-axis, I'd be at 0, -1. Then we need to go up 6. So we'd go up 1, 2, 3, 4, 5, 6, and be at 0, 5. So I'm going to put a point here at 0, 5. Let me go backwards to -1, 3. So think about if I was at -1, 3, and I flip over the x-axis, I'm at -1, -3. Then we go up 6 and go 1, 2, 3, 4, 5, 6. We are still at -1, 3. All right. There's a point that was kind of off the grid, but -2, 9. We can find the inverse of by reflecting over the x-axis. We're at -2, -9, and then go up 6. We're going to be -2, -3. Every single one of these points we can flip over the x-axis and shift up 6. We're going to see this approach the horizontal asymptote of +6. All of these transformations that we typically see can be summarized and into y equals a times b to the x power plus c. A is a vertical stretch or shrink. We've seen that happen a lot. It could also be a reflection over the x-axis. C is what shifts it up or down. So we're going to take these ideas and put them into the equation, or creating the equation from a graph. Some important exponent rules are included in the notes here because we're going to use those exponent rules as we solve equations. So these should be familiar to you already. If not, they're just here for reference. So let's look at this first graph. We can see some information already highlighted for us. We've got a point here at 0, -3/2, and then another point at 2, 5/2. So if I look at the general function, a times b to the x plus c, that plus c is what tells us if this was shifted up or down. Now I can already tell that this function was shifted down because the asymptote has shifted. The asymptote is at -2. So if the asymptote shifted, that is going to affect c. So I'm going to add some things into the notes here that hopefully will help explain and have a good resource for you later. So since the asymptote shifted to y equals -2, c would be -2. That would make the whole function move down 2. So I'm going to go ahead and write that out. Y equals a times b to the x power minus 2. Now we need to somehow figure out what a and b are, and we're going to use the y-intercept first. We use the y-intercept to find a. The point here is 0, -3/2. So that means that y is -3/2 when x is 0. I can plug in that so that I'm using that relationship to find what is going to satisfy this equation. The reason we use the y-intercept first is because of this b to the 0 power. Anything to the 0 power is 1. So this is saying -3/2 equals a times 1 minus 2, which is just a minus 2. If we're solving for a, we would add 2 to both sides. -3/2 plus 2 is +1/2. Now we know y equals 1/2 times b to the x power minus 2. We still need to find out what the value of b is. We can use another point to find b. We use another point that we can either see automatically, that we're not having to estimate, or one that was given to us. So in this case, y is 5/2 when x is 2. And I'm plugging that in for my x and y here. And we're going to solve our equation. To solve that equation, we would add 2 to both sides to undo this -2. 5/2 plus 2 would be 9/2. 9/2 equal 1/2 times b to the second power. We can divide both sides by 1/2. 9/2 divided by 1/2 would just be 9. So 9 equals b squared. And b is equal to plus or minus the square root of 9, which would be plus or minus 3. Okay, so the base of an exponential is always positive, which means b is 3. and we write our overall function. Now I'm kind of bleeding into my space for number 2, but my equation would say y equals a was 1/2 times b, which is 3, to the x power, and then minus 2. We use that same process for all of these graphs. So in number 2, I have a horizontal asymptote that has shifted up 1, so the horizontal asymptote is at y equals 1. That tells me that in my equation I have y equals a times b to the x power plus 1. We then use a coordinate like 0, 1/4. That y-intercept tells me that when x is 0, y is 1/4. We use that first because of that b to the 0 power. B to the 0 is just 1, and that's a times 1, so that would just be a. If I subtract 1 from both sides, I get negative 3/4 equals a. Then we need to plug in the other point so we can solve for b. So b is using 3, -5. X is 3, y is -5. And we're going to solve this equation. I would subtract 1 from both sides, which makes -6 equals -3/4 times b to the third. If I divide both sides by -3/4, you can use your calculator if you need to, but -6 divided by -3/4 is +8. You do want to put that -3/4 in parentheses. All right, so 8 equals b to the third power. We take the cube root of both sides and get +2. So our equation would be y equals -3/4 times 2 to the x power plus 1. So if you've got an idea of what's going on here, why don't we pause the video and try to practice number 3 and 4 on your own. This is going to require some of our algebra skills using those exponent properties, so if you need to refer back to those, you can. All right, and if you have already solved them, I'm going to go ahead and do them here. If you haven't, you can just keep going with me. We see that the horizontal asymptote is -1, so this would be y equals a times b to the x power minus 1. Everything is shifted down 1. Then we would use our y-intercept, so 0, -4. That makes this -3 equals a. And then we're going to plug in another point. So now we know y equals -3 times b to the x power minus 1. The other point we were given is 1/2 -5/2. So the y value is -5/2. The x value is 1/2. We would add 1 to both sides. Adding 1 to both sides would make this -3/2 equals -3 times b to the 1/2 power. We can divide both sides by -3. This is -3/2 divided by -3, and we just get 1/2. B to the 1/2 power uses those fractional exponents, the rational exponents. So another way to write b to the 1/2 power is the square root of b. And to undo that square root, we would square both sides. So squaring 1/2 is 1/4, b is equal to 1/4. So our overall equation would be y equals -3 times 1/4 to the x power minus 1. And then if you've already done number 4, we have a horizontal asymptote, again at positive 1 here. So y equals a times b to the x power plus 1. I'm going to plug in my y-intercept, so 2, 0, 2. When x is 0, y is 2. We would subtract 1 and get a is equal to 1. Then that would say y equals 1 times b to the x power plus 1. And I need to plug in another point. This other point is going to be negative 3 35/8. So 35 over 8 is the y when x is negative 3. We would subtract 1 from both sides. 35/8 minus 1 should be 27/8. And I get b to the negative 3 is equal to 27/8. This is where your algebra skills are going to vary and kind of lead you to which way you understand this best. But using negative exponents, we have 27 over 8 is equal to 1 over b to the 3rd power. I could cross multiply here and multiply that b to the 3rd power over and get 27b to the 3rd. If I multiply by 8, I get 1 times 8. So 27b to the 3rd is equal to 8, which means b to the 3rd is equal to 8 over 27. If we take the cube root of both sides, we get 2/3. So y equals 1 times 2/3 to the x power plus 1. And lastly, we're just going to investigate an exponential application real quick. So we have a compound interest formula that looks at what happens when you invest some money into an account that is compounded a certain number of times a year. So when we see compounded, that's going to be our clue for using compound interest. In this formula, we have a equals p times 1 plus r over n raised to the nt power. That p is your principal investment. That's however much you initially invest. N is the number of times the money is compounded each year. So you're going to see things like compounded monthly or daily, quarterly, annually, whatever, however many times it's compounded that year is N. R is our interest rate. This always needs to be expressed as a decimal. And then T would be however many years that we're working with. So in number 1, we just want to see, can we use that function? $7,520 is deposited into an account at 3.25% APR. That APR is annual percentage rate. Compounded quarterly, there's our big clue word, compounded. So this one's compounded quarterly. If N is the number of times it's compounded in 1 year, then quarterly would be 4 times a year. We're going to write the function of A, the amount of investment after T years. So that A of T would equal an initial investment of $7,520 times 1 plus R over N. 3.25% as a decimal would be 0.0325 over N, so over 4 here, raised to the NT power, which would be 4T. So here's our overall equation, and the second part of this says how much money will be in the account after 5 years. So we're just plugging in 5, A of 5. 7,520 times 1 plus 0.0325 divided by 4 raised to the 4 times 5 power. Now you want to practice using your calculator just to make sure that you understand how to type things in correctly for yours. If you have one like mine, you can kind of follow along here, but we're doing 7520 parentheses 1 plus r over n. It is helpful to use that fraction button so you don't have to worry about parentheses ever, but we have 1 plus r over n in parentheses raised to the nt power, so 4 times 5 power. This gives me $8,841.08. Since we're working with money, it would be practical to round to 2 decimal places. So $8,841.08. All right, and number 2, a money market account advertises 1.25% interest rate compounded monthly. The clue words are compounded. This one's monthly, which means n is 12. You decide to invest $4,000 into the account. What will the account balance be after 3 years? So the account balance after 3 years would start at 4,000. That's the initial investment. 1 plus r over n. 1 plus 0.0125 over 12 raised to the nt power, which would be 12 times 3 in this case. And we plug that into our calculator. So 4,000 times 1 plus 0.0125 divided by 4. Divided by 12. And then raised to the 12 times 6 power. 12 times 3 power. We get $4,152.77. There's a third question here in the notes that is an accident. This is going to be solving for t, which we'll learn later on when we talk about exponential equations. So for now, we're setting up the equation so that we can plug this into our calculator.